Hello everyone, today let's take a look at QP64 where we're proving the geometric series, and it'll be very useful in the future, right, with Markov chains and infinite kind of recursive type of things. So we let r be a real number with r not equal to 1, and we define this sum right here, and we need to show these two things. And once we show this one should be very trivial. So basically my plan for this video is to just show you how the proof works. It's actually not that hard if you know it, and then after that we can talk about why it makes sense geometrically or visually. So in part A, we're trying to find this, and basically when you expand it a little bit, our first term is going to be 1, r to the 0th power is 1, and then we're going to get r to the power of 1, which is r, and then r squared, and then r cubed, all the way up to when we add on r to the power of n. So this sum right here is equal to s sub n, and to prove that s sub n is equal to this, all we have to do basically is just multiply s sub n by r. Now obviously we can just distribute this inside the multiplication, so we can just multiply r by all of these numbers up here because we know that s sub n is equal to this, right? So we take 1 times r, we take r times r, which is r squared, and we take r times r squared, which is r cubed, and etc. We're going to get all the way up to r to the power of n plus 1. Now notice that these terms right here are very similar, so what we can do is basically take this r times s sub n and subtract off our original s sub n. And then when you do that, so I'd be subtracting all of these numbers up here from these down here, I'd basically get r minus r. They would cancel. I'd get a ton of cancellations, right? R squared minus r squared, cancel. R cubed minus r cubed, cancel. And then I'd get all the way up to r to the power of n up here, and that would cancel with this term because we'd be subtracting it. Now the only terms that would remain after all this cancellation are this -1 up here and this r to the power of n plus 1 down here. So now we know that this is just equal to r to the power of n plus 1 minus 1. Now you can see how we might get our closed form solution. We're going to factor out at s sub n from the left side. So we're going to get s sub n times r minus 1 is equal to this number up here. And then we can just divide each side by r minus 1. And we get s sub n is equal to this number up here divided by r minus 1. So this right here is a much simpler way of calculating this sum. And the reason it looks different in the way it's posed in the question is just because if you multiply the top and the bottom by -1, well then you'll get exactly that. You'll just get 1 minus r to the n plus 1 on 1 minus r, obviously. So that's how you show that, but I think the real interesting part of this question is thinking about it geometrically, like why that actually makes sense. So if I take a simple case like r equals 2, you can see that this is going to be equal to the sum of a bunch of terms. It's going to start at 1, then 2, and then 4, and 8, and 16, and etc., all the way up to 2 to the power of n. And the key thing to note is just to observe the pattern that the differences between sequential terms in our series are related to the actual series that we're trying to find. For instance, the difference between these two terms is 8. The difference between these two terms is 4. The difference between these is 2. The difference between these is 1. Now you can see in the case when r equals 2, these are related, right? These are equivalent. In the general case, this is also easy to see. If I have 2 to the power of some k plus 1 and I subtract off the term before it, well then that's going to give me, well, I can factor out 2k and I get 2k times 2 minus 1, which is just equal to 2 to the power of k. And the reason that this is important, if we look at our number line down here, is that the sum of differences is a lot easier to calculate than the actual sum itself, right? Now, why exactly is this? Well, let's say we're trying to calculate the first 5 terms of our summation, right? So these 5, we're trying to add them up. Now look at the sum of differences, right? This one right here will be 16. The difference between these two is 8. The difference between these two is 4. This is 2, and this is 1. And when we sum up the differences here, that's exactly what we were trying to find, but it's going to be a lot easier to calculate because you can just notice that we're basically calculating the length of this blue line when we sum them up. And clearly, when we're on a number line, it's really easy to see. The length of this blue line is just going to be this number, 32 minus 1 over here, right? So we know that this is equal to 31, which is in fact the sum of the first 5 terms in our summation. Then you can see if instead we wanted to calculate the sum of the first 6 terms, so everything in black here, well then now, well, we know the length of this interval right here is also 32, so we just sum all of the differences up again. We could just do that by taking 64 minus 1. So when r equals 2, the sum of the first n in this series, all we do is we take 2 to the power of n plus 1, the next term in our series, and we subtract off 1. Okay, so now let's try to think about the case when r is equal to 3. So now again, let's try to think about the sum of differences. If I have 3 to the power of k plus 1 and I subtract off the term before it, then what am I going to get? Well, I factor out 3 to the k and I get 3 minus 1. 3 to the k times 3 minus 1 is equal to 2 times 3 to the power of k. So now again, the differences between elements are related to the series itself. You see this term appearing again. It's not the same because now we have this factor of 2, but it's still there. So this difference right here between 1 and 3 is obviously 2, but that's just equal to 2 times 3 to the power of 0. This difference right here is equal to 2 times 3 to the power of 1, or 6, right? This one here is 2 times 3 squared, which is equal to 18. And then this one here is 2 times 3 cubed, which is equal to 54. So now let's say that we were trying to sum up these first 4 elements. Well, we already know that the sum of differences is a lot easier to calculate, so let's try and do it in terms of that first. So all we have to do is notice that 3 cubed pairs off here, 3 squared pairs off here, 3 to the power of 1 is obviously here, and then these are the same. So we just need to calculate the sum of these, and they're all multiplied by a constant factor of 2, so we can just divide by 2 at the end. And again, the way we calculate it is just the length of this blue line. It's just going to be 81 minus 1, which is going to give us 80, obviously. And we know that's equal to, well, we pull the factor of 2 out, and then we have 2 times the sum from k equals 0 to 4, in this case, of 3 to the power of k. So now again, all we have to do is divide each side of this equation by 2, because we know that this is what we were originally trying to find. And when we do that, we'll get that this is equal to 40, right? 80 divided by 2. So now for a general case, when r is equal to 3, all we do is we calculate the next term, which we do by taking 3 to the power of n plus 1. We subtract off 1 to get the length of the blue line, and then we just divide by 2 to get rid of this constant factor. And then you can just keep thinking about it this way, right? If we were dealing with r equals 4 instead, well, then our constant factor would be 3, and if we were dealing with 5, our constant factor would be 4, and etc., right? So now for a general r, we'd know that s sub n is just equal to r to the power of n plus 1 minus 1 divided by r minus 1, which is exactly the formula we have right here, except this one's just multiplied on both top and bottom by -1. So that's visually how you think about this formula. You could also prove it by induction, but not really worth our time. It's pretty simple, but let's go on to part B, which should be trivial now that we know this. So now in part B, instead of summing up the first n terms, we're summing up infinitely many of them. So obviously we showed in part A what the formula was for general n, so all we have to do is just think about this now as a limit as n goes to infinity of that exact same formula, right? R to the power of n plus 1 minus 1 on r minus 1. We're obviously enforcing this because if r was greater than 1, then the series would diverge and go off to infinity. Also, if r was equal to 1, this would also go off to infinity, obviously, because every single term would be 1. But we know that if we raise a number less than 1 to a really large number, this is going to approach 0, this term right here. So when we take the limit, this goes to 0, and we're left with -1 on r minus 1, also known as 1 on 1 minus r, which is more useful to think about because r is less than 1. So that's how you show that, and this infinite series one particularly is really important, and it's going to come up a lot in the future problems. And maybe one more way to just think about this, besides taking the limit, is just to understand that this is basically going to be equal to 1 plus r to the power of 1 plus r squared plus r cubed, etc., all the way up to a really large number. I'll just say actually r to the power of infinity. And now if you look at our number lines now between 0 and 1, then let's say we're dealing with r equals like 0.3 or something. Well, now if we look at the sum of differences as n goes up to infinity, obviously we're going to get 0.7 here, and then we'd get some smaller number in here, 0.3 divided by 2, and then we'd get another smaller number, and then since it goes to infinity, we'd basically end up getting the entirety of this blue line, which we know has length 1. And in the 0.3 example, our next term would be 0.3 times 0.3, or 0.09. And the difference now between successive terms in our sequence would be, for instance, if I take r to the power of n minus r to the power of n plus 1, n before n plus 1, because this one will actually be smaller now. Then I factor out r to the power of n, so I get r to the power of n times 1 minus r. So the difference here between 0.3 and 0.09 is 0.21, which we know is equal to 0.3 times 0.7. And then the difference between the next terms would be 0.3 squared times 0.7, and then the next would be 0.3 cubed times 0.7, and etc. The difference up here between 0.3 and 1 was just 0.7 times 0.3 to the power of 0. And again, we know the sum of this entire blue line is equal to 1, so what does that leave us with? Well, it leaves us with the formula that 1 is equal to 0.7, again, common factor, so we can take it out, times the sum from k equals 0 to infinity of 0.3 to the power of k. And this is the value that we're trying to find, so we know that this is just going to be equal to 1 on 0.7, which was just 1 on 1 minus r, because r was 0.3 in that example. So yeah, that's how we arrive at the same answer. I think this visualization kind of geometric interpretation is pretty cool, and that's why I included it and not just the proof.